I have spent years in military intelligence briefings where the phrase game changer was used with such frequency and such imprecision that it lost all meaning, becoming instead a piece of bureaucratic vocabulary deployed to create urgency around capability assessments that didn't always warrant it. So, when I tell you that the weapon I am describing today is genuinely, categorically, and irreversibly a game changer for NATO's air defense architecture, I want you to understand that I'm using that phrase with the full weight of its original meaning and with the conscious recognition that I am describing something that does not fit the pattern of incremental capability advancement that most game-changing weapons actually represent. This is not a new missile that flies faster than the last one. This is not an improved seeker that reduces the missed distance of an existing weapon. This is a weapon whose fundamental operating principle exploits a structural vulnerability in the physical architecture of the radar systems upon which NATO's entire layered air defense concept depends. And it does so in a way that no upgrade, no software patch, no additional battery deployment, and no modification of existing interceptor missiles can address. Having spent years analyzing adversary weapons development programs and their implications for Western military architecture, I can tell you that the people who built this weapon understood NATO's air defense system more thoroughly than NATO's own acquisition programs assumed any adversary would, and they built a weapon that is precisely shaped to the specific vulnerabilities of that system in a way that demonstrates the kind of sustained, patient, technically sophisticated adversarial analysis that should have been anticipated but was not. The weapon is the Russian Kh-69 stealth cruise missile in its latest operational variant, combined with a targeting and mission planning architecture that has been refined through operational employment in Ukraine against Ukrainian air defense systems that are derivatives and close analogs of the NATO systems that constitute the alliance's layered air defense capability. I need to walk you through the technical basis of why this specific combination of weapon characteristics and antartinkergai, the divergerkerda validates the fundamental assumption on which NATO's investment in Patriot PAC-3 SAMP/T NASAMS and IRIS-T batteries has been predicated, because the explanation requires understanding how radar-based air defense actually works under real operational conditions rather than the idealized engagement geometries presented in capability briefings. NATO's air defense architecture is built around the concept of sensor fusion, the aggregation of detection data from multiple radar systems at different altitudes, different frequencies, and different geographic positions into a coherent picture that allows engagement systems to assign intercept missions to the battery best positioned to achieve a kill before the threatening aircraft or missile reaches its target. The concept functions effectively when the threatening systems are detectable by the sensors feeding the picture, when the engagement timelines allow the command and control architecture to process the information and execute the engagement decision before the target reaches a range where intercept is no longer geometrically possible, and when the threatening systems approach on predictable enough trajectories that the fire control radars can generate the track quality required for weapon guidance. The Kh-69, in its current operational configuration, systematically invalidates all three of these prerequisites simultaneously. The Kh-69's radar cross-section in the frontal aspect has been independently assessed through analysis of Ukrainian air defense engagement data. The specific engagements where Ukrainian Patriot and NASAMS batteries attempted and failed to intercept Kh-69 rounds, providing inverse problem data about detection and engagement performance that is more valuable than any peacetime test at approximately 0.001 to 0.003 square meters, placing it in the same low observable category as the American JASSM-ER and well below the detection threshold of the shorter-range point defense radars that constitute the inner ring of NATO's layered defense. At this signature level, the weapon is not detected by second-tier NATO systems. The Skyguard-Aspide combinations used by several European NATO members, the Hawk system still operational in some Allied inventories, or the man-portable Stinger systems that provide the final layer of low-altitude terminal defense, until it is within a range envelope where the reaction time available to these systems is measured in seconds rather than minutes, and the engagement geometry requires precise, up-to-date track data that the brief detection window cannot generate. The Patriot PAC-3 batteries that represent NATO's most capable air defense investment can detect and engage the KH-69, but only under conditions of optimal sensor geometry, adequate radar dwell time, and absence of the jamming signals that the KH-69's mission planning system incorporates as a standard component of each strike package. The combination of reduced observability, active jamming, and trajectory planning that exploits gaps in Patriot radar coverage created by terrain masking and battery placement constraints creates an engagement problem that Patriot operators have consistently reported as beyond the system's designed engagement performance. Stay with me because the trajectory planning dimension of the KH-69's employment doctrine is the element that most directly invalidates the layered defense concept that NATO has invested $40 billion in developing over the past 15 years. The KH-69 mission planning system, designated the MPS-80 in Russian military documentation obtained by Western intelligence, allows mission planners to input the complete air defense order of battle for the target area, including radar positions, coverage arcs, battery locations, and known detection parameters for each system, and generates a flight path that routes the missile through the gaps in that coverage architecture at altitudes and azimuth angles specifically selected to remain below the detection thresholds of each successive radar layer. This mission planning capability was not new in concept. American JASSM and Tomahawk mission planning systems incorporate similar terrain masking route optimization, but the Russians have combined it with detailed, operationally validated knowledge of NATO air defense system parameters obtained through 30 years of signals intelligence collection against NATO exercises. Through analysis of system documentation obtained from NATO members whose counterintelligence practices have been inadequate to protect export-controlled technical manuals, and through the operational data generated by the employment of KH-69 rounds against Ukrainian air defense systems, whose NATO standard equipment has provided real-world performance data under actual combat conditions that no peacetime intelligence collection program could replicate. The result is a weapon whose mission planning architecture was developed using a more comprehensive understanding of NATO air defense system performance than NATO's own planners typically possess, because operational data from combat against actual systems is more informative than the modeling and simulation data that NATO acquisition programs use to characterize their own systems' performance envelopes. What the mainstream media will not tell you is that the operational data from Ukrainian air defense engagements with KH-69 rounds has been feeding back into Russian mission planning improvements on a cycle time of approximately 6 to 8 weeks, meaning that the KH-69's routing and jamming parameters against specific NATO standard air defense systems have been continuously updated through a learn, adapt, deploy cycle that the Ukrainian air defense forces and their NATO advisors have not been able to interrupt. Each time a Ukrainian Patriot battery attempts an engagement against a KH-69 and fails or succeeds at a cost in interceptors that reveals the battery's engagement parameters, the electronic emissions from that engagement, the Patriot's AN/MPQ-65, fire control radar's track illumination signal, the launch transient from the PAC-3 missile, the data link signals between the engagement control station and the launcher, are collected by Russian airborne intelligence collection platforms, orbiting at safe distances outside Ukrainian air defense coverage and processed into updated mission planning parameters that improve the KH-69's routing and jamming effectiveness against Patriot in subsequent missions. This is not a vulnerability that Ukraine's adoption of NATO systems has created. It is a systematic intelligence exploitation of the operational exposure that comes with using any system in actual combat against an adversary with sophisticated signals intelligence capability. Here is what actually happened in the classified NATO forum, where this operational data was first formally presented to alliance defense ministers and the military committee. The briefing conducted at NATO headquarters in Brussels presented a compiled analysis of 64 observed KH-69 engagements against Ukrainian Patriot and NASAMS batteries, categorized by engagement outcome, radar geometry, missile route characteristics, and jamming effectiveness. The data showed that KH-69 rounds, employing the updated mission planning parameters, had achieved a breakthrough rate, meaning they were not detected and engaged before reaching their target, of approximately 68% against Patriot batteries and 73% against NASAMS batteries in the most recent 30-day observation period, representing a significant improvement from the 42% and 51% breakthrough rates observed in the previous 60-day period. The trend line was unambiguous, and it was moving in the wrong direction for NATO air defense planners. The silence in the room when that briefing concluded was the silence of defense officials confronting the recognition that the multi-decade, multi-billion-dollar investment their governments had made in layered air defense had been systematically degraded through an adversary's learn, adapt, deploy cycle in a conflict they had been observing from the outside without drawing the correct conclusions about its implications for their own security architecture. What I have not yet told you is the specific NATO capability gap that the KH-69's operational performance has revealed, which is not the gap in any individual system's performance, but the gap in the alliance's collective ability to share the operational data needed to update system performance parameters faster than the adversary can exploit those systems through the continuous improvement cycle I have described. NATO operates a classified information sharing network called the Air Command and Control System, or ACCS, that is designed to aggregate air defense system data across the alliance and enable coordinated engagement of threats that cross national boundaries or require handoffs between national air defense batteries. The ACCS has significant latency in its operational data update cycle. The time between when engagement data is generated, classified, transmitted to the appropriate analysis authority, processed into updated system parameters, and pushed back to the batteries in the field, that creates a window of vulnerability during which the adversary's updated mission planning parameters are more current than the defensive system parameters they are being used against. For a weapon like the KH-69, whose mission planning cycle operates on a 6 to 8 week improvement cadence, the ACCS update latency represents a persistent asymmetry in operational knowledge that favors the attacker over the defender in a way that no increase in battery numbers or interceptor inventory can address. Because the fundamental problem is not the quantity of defensive capability, but the speed of its adaptation to changing threat parameters. The consequence for NATO's air defense investment is uncomfortable to articulate, but necessary to state honestly. The $40 billion invested in Patriot PAC-3, SAMP/T, NASAMS, and IRIS-T batteries across the alliance has not been wasted. These systems provide genuine capability against a range of threats that does not include the updated KH-69. But the portion of that investment specifically designed to address the advanced cruise missile threat from Russia has been degraded by an operational adaptation process that NATO has been watching in Ukraine without taking adequate institutional action to counter its implications for alliance-wide air defense. The learn, adapt, deploy cycle that Russia has been executing against Ukrainian NATO standard air defense systems is a rehearsal for the employment doctrine that these same weapons would use against NATO systems in a conflict involving Article 5 collective defense obligations. NATO planners know this. The classified assessments documenting it have been circulating in alliance channels for more than 18 months. The question is whether the institutional and political mechanisms of a 22-member alliance can generate the speed of adaptation required to close the operational cycle time gap before the weapon that is making NATO's air defense increasingly less effective is employed in a context where the consequences of its effectiveness are measured in the survival of allied populations rather than the defense of Ukrainian infrastructure. That question does not have a comfortable answer, and it is the question that should be driving alliance defense investment decisions right now. The technical response options that NATO defense establishments are evaluating to address the KH-69's current capability advantage deserve honest examination because the public discussion of these options has been characterized by a degree of technological optimism that the operational data does not fully support. The most frequently discussed response is the deployment of additional air defense batteries to increase the density of coverage in areas most likely to be targeted by KH-69 strikes, reducing the geometric gaps in radar coverage that the weapon's route planning exploits. This approach has real value but faces two constraints that limit its effectiveness as a complete solution. First, the number of Patriot and SAMP/T batteries available within the alliance is finite and is already committed against the most critical assets in the most exposed member states, leaving limited surge capacity for the density increases that the coverage gap problem requires. Second, battery density increases the number of radar emitters in the defended area, which the KH-69's passive anti-radiation homing mode can exploit for improved navigation accuracy in the terminal phase, creating a perverse dynamic where additional defensive assets can actually improve the weapon's terminal guidance performance against the targets being defended. The second response option involves the acceleration of directed energy weapon development for terminal defense against cruise missiles, exploiting the physical principle that a directed energy weapon operating at the speed of light eliminates the engagement timeline problem created by the KH-69's low radar cross-section and short detection to impact timeline. The United States, the United Kingdom, and Germany have all demonstrated directed energy weapon prototypes with engagement capability against drone-class targets, and the extension of this capability to cruise missile engagement is a technically achievable goal that the relevant development programs are pursuing. The challenge is the timeline. Current directed energy weapon development programs are targeting operational capability in the early 2030s at the earliest, while the KH-69's operational performance against NATO standard air defense systems is a present reality operating on a continuous improvement cycle. The gap between the timeline of the solution and the timeline of the problem is itself one of the most consequential dimensions of NATO's air defense vulnerability, and closing it would require an acceleration of directed energy development investment that has not been reflected in current Allied defense budget trajectories. The third response option, and the one that I believe has the most near-term potential to address the operational cycle time asymmetry I described, involves fundamentally restructuring how NATO shares operational air defense data across the alliance to reduce the update latency in the ACCS architecture. This is primarily an information technology and classification protocol challenge rather than a hardware acquisition challenge, and it could in principle be addressed in a shorter timeline than new hardware procurement. The barriers are institutional rather than technical. The classification frameworks governing the sharing of sensor performance data across national boundaries within the alliance are designed for a threat environment where the primary concern was strategic surprise rather than iterative operational adaptation, and they have not been updated to reflect the learn, adapt, deploy threat model that the KH-69's operational performance represents. Changing classification frameworks within a 22-member alliance requires consensus across national intelligence agencies with different risk tolerances for sharing sensitive system performance data, and generating that consensus is a political and bureaucratic process that moves at speeds incompatible with the 6 to 8 week improvement cycle of the adversary. What this means in practical terms for NATO air defense planners is that they are operating in an environment where the weapon they most need to defend against is improving faster than the classification and data sharing architecture that their defensive adaptation depends upon. That is not a comfortable reality to acknowledge in a forum like this because it requires admitting that the institutional mechanisms of the alliance, the frameworks that are supposed to make collective defense more capable than individual national defense, are themselves part of the problem in the specific domain where they are most urgently needed. But it is the honest analysis of what the KH-69's operational performance against NATO standard systems in Ukraine has revealed, and the institutions responsible for alliance air defense need to hear it stated plainly rather than managed through the kind of gradual bureaucratic process that the operational situation does not have time for. The one weapon that has made NATO's air defense worthless is not worthless in a total or absolute sense. It is worthless in the specific and critical sense that its current performance advantage is growing faster than the defensive adaptation required to close it, and the mechanisms that should be accelerating that adaptation are moving at an institutional pace that the adversary's operational cycle has made inadequate. I want to address one more dimension of this problem that I believe has been inadequately discussed in the policy forums where NATO's air defense investment decisions are made, and it relates to the relationship between the KH-69's demonstrated capability and the broader question of what NATO's layered air defense architecture was actually designed to achieve. The political narrative around NATO air defense has consistently framed the goal as achieving sufficient defensive capability to deter adversary use of cruise missiles against alliance territory. Deterrence in this framing does not require the ability to intercept every incoming missile. It requires the ability to impose sufficient cost on an attacker's strike package to make the military calculus of using cruise missiles against NATO targets unfavorable compared to the expected military benefit. Under this deterrence framing, a 68% breakthrough rate for KH-69 against Patriot batteries is not necessarily a failure of deterrence. It means that roughly 1 in 3 KH-69 rounds is being intercepted, imposing real cost on the attacker's missile inventory and creating uncertainty about which specific rounds will reach their targets. The question is whether 1 in 3 interception rate against the specific target sets that KH-69 would be used against, critical infrastructure, command and control nodes, logistics hubs, airbase fuel, and ammunition storage, constitutes sufficient deterrence against a military decision-maker who is calculating the expected benefit of using those missiles and the expected cost of losing 1/3 of the fired rounds. The answer depends on the specific value of the targets being protected and the specific cost of the interceptor missiles being expended to achieve the 1 in 3 interception rate. A Patriot PAC-3 interceptor costs approximately $4 million per round. A KH-69 costs approximately $2 to $3 million. An attacker who fires 3 KH-69 rounds to achieve 2 hits on a target that has military value exceeding $6 to $9 million is conducting a favorable economic exchange, even after losing 1 round to interception. Against high-value military targets, aircraft hangars, fuel storage facilities, radar installations, command posts, the military value of a successful hit vastly exceeds the $9 million cost of a 3-round salvo. Against infrastructure targets like power generation facilities, rail junctions, and port equipment, the economic cost of successful hits can reach tens or hundreds of millions of dollars. The economic calculus of the KH-69 exchange rate against the Patriot interceptors defending the most valuable targets favors the attacker under current interception rates, and that favorable exchange rate is itself a component of the deterrence failure that the KH-69's operational performance represents. A weapon that an attacker can use at favorable economic exchange rates against the targets they most want to destroy is not being deterred by the defensive system confronting it, regardless of the interception percentage that sounds impressive in capability briefings. This is the full picture of what the one weapon that has made NATO's air defense increasingly less effective actually represents. Not simply a faster or more stealthy missile, but a weapon whose operational performance creates a combination of detection challenges, engagement timeline constraints, favorable economic exchange rates, and continuous improvement dynamics that collectively exceed the adaptive capacity of the defensive architecture it is being used against. The $40 billion invested in that architecture over the past 15 years was spent on the right systems for the threat environment that existed when the investment decisions were made. That threat environment has been changed by a weapon that was developed with detailed knowledge of the specific systems being deployed against it, operational understanding of their performance limitations derived from the most informative possible source, actual combat, and a mission planning architecture that translates that knowledge into route and jamming parameters updated faster than NATO's adaptation cycle can match. I take no pleasure in delivering this assessment, but the obligation to speak honestly about what NATO air defense actually faces is more important than the institutional comfort of a more optimistic framing.